Good morning, my YouTube viewers. It is Crystal here. I'm just here this morning because I want to give you a code review. This code review is going to be on the tweets, but it's going to be using a recurrent neural network instead of a sequential network. So basically what I did was I was hoping to improve the accuracy of the tweets if I used RNN. So now what we're going to do is we're going to use an RNN, and we're going to see how much the accuracy has improved using an RNN. So I wrote this program in Google Colab, which is a great program to use because you can do everything in your browser. You can do everything online and in the browser. So that's good. And the only bad thing about Google Colab is the fact that it doesn't have a very good undo function. So you have to be very careful not to not to accidentally overwrite or delete any information, any code, which is what I have done in the past. If you do accidentally delete or overwrite code, you can always go into the save history and you might be able to get the code back that way. But I have been able to get my code back in the past, but sometimes you can't. So that's just something you need to be aware of. So after we've created the program, what we want to do is we want to import the libraries. So the libraries that we imported were NumPy as NP, which is for numerical computations. We're going to import Pandas as PD, which is to create a data frame and data processing. We're going to import matplotlib.pyplot as PLT, which is data visualization. We're going to import Seaborn as SNS, which is some more data visualization. We're going to import Re, which is an inbuilt program to do string processing, and we're going to import String, which is an inbuilt program which does string processing as well. We're also going to import sklearn, which provides machine learning functionality, and we're going to import Tensorflow, which creates the neural network and does the other things. So Tensorflow is a very big library, and obviously I'm learning it, and it's different from sklearn. It's because in sklearn, if you look up a word, then it comes up with a whole big list of functions that you can use. But Tensorflow is a little bit different. You look up a word and then it directs you to a page in the internet to look at. So that's the difference between sklearn and Tensorflow. I think sklearn is more like a toy library, but I think the documentation on the library is easier to read than Tensorflow is. So after we have imported all of our libraries, we're going to read the CSV file using Pandas. So df equals pd.readcsv. You give them the link address, the website address for the CSV file, and df equals df drop id because it had an ID in it, and the ID isn't necessary. The reason why the ID isn't necessary is because every row is indexed in the data frame anyway. And then you've got your DF. So here's your DF with your label and your tweet, and your label is going to be your Y variable, and your tweet is going to be your X variable. Now what we're going to do is we're going to use sklearn we're going to use Seaborn to analyze the tweets or the labels. And so you can see that you've got a very big class imbalance here. You've got just a few ones and lots of zeros. So you've got a class imbalance to work on. So we're going to do a value counts. you've got 29,720 zeros and 2,242 ones. So that shows you what your class imbalance is, and you've got two classes. We're going to split the data set. So your X variable equals DF tweet, your Y variable equals DF label, and then we're going to use sklearn to split the data set up into training and validation sets. And then after we split the data set up into training and validation sets, we're going to convert those training and validation sets into tensors. Now what we're going to do is we're going to vectorize the data. So we're going to create a function and call it def custom summarization. So everything is going to be lowercase. And then you're going to strip the break, and then you're going to replace all of the unusual characters with space. So max features equals 10,000, sequence length equals 250, and now we're going to use TensorFlow's text vectorization to define text vectorizer. So standardize equals custom standardization. That's this function right here. Max tokens equals max features. Output mode equals int. Output sequence length equals sequence length, and you've got sequence length here. So now what we're going to do is we're going to make a text-only data set without labels and call it depth. So you have to use a depth. Whenever you use text vectorizer, you have to use a depth. So features equals xtrain ds. Because we've only got xtrain dx as your x variable. And then text vectorizer dot adapt features. So then we're going to adapt the features. Now we're going to get the vocabulary. Vocab equals np array. Text vectorizer get vocabulary. So you get the vocabulary. So you can see you've got a few unknown words in there. And now we're going to process it. And that's a function that we created to return the vectorizer. And now what we're going to do is we're going to encode the example. So text vectorizer encoded example equals text vectorizer xtrain ds, and we're going to use 3 coded examples numpy, and then you got your coded example with a bunch of zeros. And then we're going to create a for loop. For n in range 3, print original, and then print round trip. That's your vocab encoded example. So original equals your welcome teammates dance to the tune of joyfulness. And the round trip is your welcome teammates dance to the tune of unknown. And the original is enjoying the sunshine at #sunshine. And then round trip is enjoying the. Original is finally it got framed, thanks Georgina Drake. And round trip is finally it got unknown, thanks unknown football. So that's your original and your text vectorized. So now what we're going to do is we're going to define our model, and in this instance it's going to be an RNN. Or that's the code that I got as it being an RNN. So model equals tf.keras sequential, use text vectorizer, tf.keras layers embedding, so you've got input dim, and then output mask 0, tf.layers bidirectional, tf.layers lstm, tf.keras.layers dense, activation equals ReLU, tf.keras.layers dense equals 1, so it's going to have one output. So print layer dot supports masking for layer in model.layers, and it says false, true, 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 true. And now what we're going to do is we're going to compile the data into the model. So model.compile, loss equals tf.keras.losses, binary cross entropy from logits equals true, optimizer equals tf.keras.optimizers.atoms.1e minus 4, metrics equals accuracy, and then you do a summary of the model, and so you can see the summary. And then these are just some plots of what the model looks like. This is another plot of what the model looks like. So now what we're going to do is we're going to train the model. So epochs equals 10, early stopping equals early stopping, brackets, monitor equals val loss, mode equals min, patience equals 25, verbose equals 1. MC equals model checkpoint, and its best model TF, monitor equals val loss, mode equals min, save best only equals true, and then now it's training it. History equals model.fit, xtrain ds, ytrain ds, epochs equals epochs, validation data equals xtrain d, xval ds, yval ds, callbacks equals early stopping, comma MC, verbose equals 1, so it goes through 10 epochs. Then history loss is 10, and then history dict equals history.history, history dict key, so your history dict is your loss, accuracy, val loss, and val accuracy. And now it evaluates the model, but it can't evaluate the model in this instance because the way that this particular function works is it takes the X and the Y and combines those into one data set. And I hadn't done that in this data set. So it doesn't work in this particular program, but I kept the code in there. Okay, now we've got some more graphs that we're going to plot. So we've got a graph where you've got training loss and validation loss, and you can see that the loss increases through the epochs. And then we've got training and validation accuracy. So you can see that the validation accuracy sort of like stays same at 96, whereas the training accuracy is almost 100%. So probability model equals keras.sequential model, comma, layers.activation sigmoid. And let's come over here. And then we do ypred equals probability model dot predict x val. And then so this is your, and then ypred equals ypred greater than 0.5 dot s type in 32, and then you flatten ypred, and then you get a bunch of zeros and ones. And then so we just look at it using Seaborn. So on Seaborn you've got a bunch of zeros and a few ones. And then we check the accuracy, and we have a 95% accuracy on this. Put it under a confusion matrix. So you can see that you've got 135 ones and 78 zeros that should have been ones. And then we save the model as tweet model. So that's how you use it. And that's it. That's it for this code review. That's it for the code review. So I'm going to go ahead and conclude this video because we talked about the code review. And this is an RNN, Recurrent Neural Network. And it did actually improve the accuracy of the tweets a little bit. So thank you so much for watching my video. If you like my video, please like, subscribe, and share. thank you to my subscribers for supporting my channel, and if you like my video, please like, subscribe, and share, and I look forward to making more code reviews for you in the future.